Hi, and welcome back to the course on distributed systems and security. It's about time, the lecture of Synchrony. We have talked a bit about physical time and clocks and how we can synchronize clocks. So let's now allow ourselves to assume that we have a distributed system with several computers and they have reasonably synchronized clocks. Okay? Then I would like to introduce the notion of a round-based protocol and give a couple of examples of how we can use round-based protocols to do interesting things. And then we look at a round-based protocol called Strong in the next video, which is quite interesting. It's a protocol for broadcast, but I'll actually close the present video a little bit talking about a special case of that Strong protocol. So the setting is the following. So we're looking at something like, let's say, state machine replication. I have a service that's important to me, so I put it on 4 servers instead. And then I would like the system to be up and running and consistent as long as, say, at most one server is crashed at a time. When doing that, trying to keep these servers consistent, turns out it's quite convenient if we can have the computation progress in rounds, where in each round, each server sends a message to each of the other servers. Say, exchanges, what do I consider being the inputs to the system now, what state am I in, and so on. So in each round, you get inputs from everybody, does a computation, and then send output to everybody. What we would like then is also, to put the time lengths of the rounds so liberal that if in some round I don't hear from a server, I know it's because it's crashed, okay? Because this model, the setting at least here with state machine replication, right? It's about trying to replicate a service and tolerate crashed servers or Byzantine servers, okay? So I would like some kind of guarantee that if in a round I didn't receive a message from server 3, it's actually because server 3 is crashed. Or maybe it's Byzantine corrupted and it decided to not send me a message. That's even worse, right? It decided not to send me a message, but to send a message to someone else and wants to confuse us. So, the present video is basically about just going through some very basic considerations in how should we set this timeout such that I can make that conclusion, okay? That's all there is to it. And then a little warning about using time for such a conclusion later. What could go wrong if when I don't get a message, then I conclude that the sender is corrupted and kind of push them out of the protocol. So the first thing we see is that I will definitely need to make an assumption on the max transfer time of messages, right? So if I want to make the conclusion that if I don't hear from server 3, it's because server 3 is crashed. Then I need to know how long it takes for a message to travel, right? If it takes a year, I need to wait a year to see if I get the message. Yeah. That's assumption 1. We'll need to make an assumption on how long it takes to send a message on the network we are on. I also need to make an assumption on how far our clocks can drift, okay? The reason for that is, of course, if a message is to be sent at a given point in time, the sender will send it at 12 o'clock, say, on the sender's clock. But if I'm 1 hour ahead, when the message is sent, it's already 1 o'clock on my watch. So if I think it takes 10 minutes to send a message, then 10 minutes past 12, I would say, I didn't get the message. And therefore conclude that server 3 is corrupted. But it wasn't. It was just my clock ahead. So I kind of called the timeout way too early on the sender's clock. So we need to be able to implement something like this. We also need an assumption on max drift. Fortunately, we already discussed a little bit how to synchronize clocks well enough that we can assume some upper bound on how far are the clocks in the system away from each other. The only warning being that if my max drift is at most 1 minute from physical time, the max drift between two clocks in the system could be 2 minutes because we could drift in different directions. But we'll adjust for that later. I will also need, if we go in rounds with some fixed length, let's say one round is 10 minutes, I will need also an assumption on how long the computation done in each round will take. So if I'm going by rounds of 10 minutes, and in some round I ask one of the servers to do a computation that takes 10 hours, of course it won't be ready to send the message before the round is over. So I won't get the message. And I'll conclude that the server is corrupted. It's not, it's just slow. So we also need to make sure that, that the computations we're doing, that we can always do that before the next server is going to call a timeout because we didn't send something. It's getting cumbersome, right? This is why in general we like to not use time in distributed systems. We're not done, by the way. We finally need to do a synchronized start. So if we're going through rounds of 10 minutes, we also need to know when is the first round. If all of us start the computation today, but you start the computation tomorrow, and the first timeout is 10 minutes, and we didn't hear from you, so you're corrupted. No, you're not. You just wasn't informed when the protocol was to start. But that's it then. That's the 4 assumptions we need, and then we can actually do it. So we need max transfer time, max drift time on the clocks, max computation time for each round, synchronized start time. And then the algorithm is just the following. Okay, so we can compute a round length, which should be the transfer time, 2 times the max drift time, plus the max computation time. That's how long we will make each round. Then we say that each round starts on the local clocks at the start time plus n times the round length. So round 0 apparently is the first round, and it starts at start time. So on. And then what each party will do in a protocol like this here is it has some kind of function here, the round function, which describes what is the computation being done in the protocol. The protocol should do something interesting. We just encapsulate that into the round time there. So the round function. The round function takes the name of the round 7, the identity of the party, you are party 3 in round 7, and then the inputs that arrive in that round. You can use the input from yourself to keep a state. Okay? And then it will output the n outputs for that round, where y1 is going to go to party 1 up to yn here, that's going to go to party n in that round. And then we just run in rounds like that. Okay? And importantly, if by round start, I have no incoming message of the form the round number from party j to party I, the message xj, then I'll just substitute it by no message. This is where we use the timing assumption strongly and say, if I didn't get a message from you in this round, party j, I'm going to assume that you intended to send me no message. It can just be the empty string or something like that. So I do that at each round start. Then I apply my round function. I get some outputs. And then I send yj here to pj and send along that, tag it by which round it's for. Okay? And then it's very easy to see the following theorem, that no honest message will ever be substituted by this no message thing. Right? And why is that? It's because at round n here, all the honest parties will start running their round. Then they will compute this function here. That will take maximally that much time, namely computation time. Then they will send this message to everyone else. That will take max trans time. And then we have to adjust for the fact that the clocks my clock and the receiver's clock both could have drifted at most max drift away from the clock. So the receiver won't get it after max comp plus max trans time. Yeah, well, they will, but the clock might be different. So I send it too late on that clock, but at most this much late. So they will receive it no later than the sending time on my clock plus that stuff here. Right? And that was exactly the round length. So that means the message I send here, if I'm an honest server, will arrive at the receiver before they start the next round, and therefore this thing will never happen. My message will be inputted on the other side in that round. So that's all there is to it. Okay, this is kindergarten arithmetic, but it's just nice. I mean, to go through it and kind of set up the rules for what is a round-based protocol before we go into the complications of Dolive-Strong in the next video. Okay, so that's really what there is to it. So try to forget the complexity now and then just kind of get into the mode where we will just say, we now look at protocols that proceed in rounds. And in each round, each honest party have time to send a message to each other honest party. In particular, if I don't get a message, I know the sender is corrupted. The server intended me to not get the message. That's kind of the mode will be. Now, of course, we could have made a mistake and said, let's say, for example, max transfer time too low. So we said all messages on the internet, they travel, doesn't take 2 minutes for a message to travel. So we have set this thing to be 2 minutes. And then at some point it happens that one of the servers in the protocol, it's a laptop and it runs out of power. So this, I mean, the system administrator needs to find a cable, put it in, boot it up again and start it. And that took 10 minutes. Well, then it took 10 minutes to send that message. He comes up again, the round progressed, and then his message was lost. We say the message was overwritten because we were too optimistic in this transfer time. So we see that if we do that, then a message delay could actually be turned into a message loss, right? Because we progress. That's what the round-based model is. We call some timeouts, at which point we just say the message was not there, so it's lost. I'll show you a warning later how that can be dangerous. In particular, if we think of the party sending the lost message as still being honest, if we still want to take care of the safety of that server, then the round-based model could become dangerous. More about that later. So leading a little bit forward and talking about what we talked about in the introduction, I would like to then dive a little bit into the difference here between the eventually synchronous model and then the fully synchronous model, which is the one I have described for you here with the round-based one. So in the round-based model, we make this assumption that if I do not get a message, it's because the sender is crashed, the sender is corrupted, the sender is bad. We're not going to take care of this server in the algorithm. And then we had this eventually synchronous protocol where we said we assume an upper bound on message delivery, but we only assume that messages get delivered that fast often enough. It might happen that even a good process have a message that is slower than that. And that in particular means we're not allowed to base safety properties on this thing. And in such a model, what we would call the eventually synchronous model, we would not be allowed to make the conclusion that if I didn't get a message from the server, it's because it's crashed. It could just be that the message is actually slow. And then if we program a model like that, and we'll get back to that, then we would have to make sure that we don't violate safety when a message is slow, but keep safety properties always, and then make sure that we just have liveness. So in the periods where messages travel fast, where all messages get exchanged before the deadline, the timeout, we would do something meaningful in the protocol. We would make progress. Okay, that's a much safer way to program in real life, but that's not where I want to be now. I want to be in like the aggressive round-based protocol where only bad people don't have their messages arrive before the timeout, because didactically it's a nice place to be. And that's where we can look at a protocol like Dolive-Strong, which will give us some interesting insights about creating consistency in a system under Byzantine attack. Okay, that was a lot about that. And this is what I already said, that in the fully synchronous model, which is the one we're looking at now, a lost or overwritten message might violate safety. And I would like to give you an example of that. And it's also going to lead up to the next video on broadcast in the synchronous model. So let's first look at an application of a round-based protocol. I would like to use a round-based protocol to implement broadcast. And it's broadcast in the sense of Byzantine broadcast. I would like to send one message to several receivers. And I want to ensure that they receive the same message, even if the sender is corrupted, and try to confuse them. So it should not be possible to send 7 here and 8 here. So they need to compare somehow. But of course, when they compare, it could be this guy lying instead. And I don't want that to prevent this guy from outputting what I sent him. If I send 7 here and I'm honest, and this guy claims to have gotten 8, this guy over here should still output 7. It turns out to be exquisitely complicated. So let's first try to formalize what is it we would like to obtain. Now, even before that, when would such a thing be convenient to have? For example, again, if we're replicating a process, I want the same process to run on several machines. Then when a client needs to give input to the process, it's quite important that we give the same input on all 3 instances to keep them consistent. I want to have an exact copy of my process on 3 different machines, such that if one of them crashes, I can go and read the 2 other ones. And even if one of them become Byzantine corrupted and lie about what the current state is, I can just ask all 3 of them and then take majority and trust the 2 that say the same thing. Right? That's the world I would like. And then it's important, of course, that they don't become inconsistent because they run on different inputs. And it's easy to see that what we need then is exactly this thing here. Okay, so the thing is the following. So we have n servers. Some of them might be bad and do bad stuff later. One of them we'll call the sender, just arbitrarily, let's say it's this one. The sender has an input m for message. And then the other servers, we call them the receivers. And they will at some point have to output a message mi. And then we require 3 properties. First, there's a termination property which says, if all honest servers start running the protocol in the same round, then all honest servers will also output something eventually. Let's just say for now, they will do it in the same round. So after 7 rounds, then output something, okay? So there's a promise here they get started in the same round, but then they have to promise to also stop and output something. Okay? That means now each of them will eventually have a well-defined mi, whatever they outputted. And then we require a relation between these MIs for this protocol here to be good to solve the problem for us. Maybe we start with the agreement one. We say that if 2 honest machines, 2 machines that were not taken over by an adversary and did not crash, so 2 correct machines, if they output mi respectively mj, I require that those 2 messages are the same. Okay? That means if we're looking at the state machine replication setting, where I have a service running on 3 different servers, that even if something bad happened, even if the sender is corrupted, it's always guaranteed that the honest ones at least run on the same input. That's good. So now they stay consistent. This we could easily get by just always having the output be 0, 0, 0, 0. So we also say the protocol should be meaningful, which is often what we call validity in these trace properties that we're giving. Namely that if the sender is honest, if S1 is really honest and runs the protocol correctly, of course the protocol should also output the message that the sender intended to send. Okay? And if you take both of them, then we see that in a setting where the sender is honest, it means that all the honest servers will output exactly that message in the agreement. So agreement only makes sense as an extra property when the sender is actually corrupted. So it says that a corrupted server can send whatever it wants, but the honest servers must output the same at least. Okay? I hope it's clear what we're trying to do, and I'll return to this in the next video in greater detail. Here's a protocol that's doing this, and it's for the round-based protocol, for the round-based model. I'm going to look at a very specific setting where I have exactly 3 servers, and up to 2 of them can be corrupted. It could also be that only 1 is corrupted and no one is corrupted. And I'm looking at Byzantine corruptions. So it could be that one of the servers is really trying to break one of these safety properties we had, either validity or agreement. But let's first look at what the protocol is. So in round 1, the sender will send the message to everybody. And then it will send along with the message, it will send a digital signature on the message. So let's assume we have a PKI, that somehow we all know each other's verification keys for a signature algorithm, as you saw in the video on authentication. So that means the sender can sign the message such that, you know, when it gets relayed, it's not possible to lie about what message you got from the sender. And then what the 2 other servers will do now, S2 and S3, they'll just take whatever they got from S1 and then swap it. So they'll tell the other one what they got. It could be that they got nothing, and then they'll just claim that they got nothing. It could also be they're cheating and got something, and then claim that they got nothing. There's nothing we can do about that. But what they can't do is get like the message 42, and then they claim that they get 43, that they got 43, right? Because they have to send a signature along on 43, and they can't. They only have a signature on 42. Now, of course, if the sender is corrupted and was stupid enough to sign 42 here and 43 here, then when the 2 honest servers swap it, they will see that they have 2 different signed messages, and that's clear that that can only happen in one way, namely the original sender was corrupted. And then they will just, let's say, output no message, okay? It could also be that none of them got anything, so when they exchanged, they saw no signed messages at all. And the kind of the most concise way to describe the algorithm is simply to say, you get a signed message, and whatever you got, nothing or 1, maybe even several ones, you send that to the other one, and the other one does the same to you. And then you look at the total set of signed messages you received so far. If there's a single one, that is the one you will take as output. If there's 0 or 2 or more, you will just output no message. So that is the algorithm. I'll let it stand for a second so you can take it in at what's going on. And then on the next slide, try to argue why this works. Now, this might very well be the first time we argue in some detail that an algorithm works. So let's just make a meta comment here and say the way we will do it in general, I mean, it's just we have typically just defined, what do we want the protocol to do by a list of these trace properties, termination, validity, and agreement here. And then you just go over each of them and verify them. Boop, boop, boop. So what was it we wanted this protocol to do? Well, it should have termination, validity, and agreement. So let's just check them. Okay, termination. It said that if all the servers start running in the same round, they will stop at some point. Well, they do. They stop in round 3 because send a message, exchange it, output. Okay, so that's termination. Check. Validity. We wanted the protocol to have the property that if the sender is honest, then all honest servers will output the message that the honest server intended to send. Remember that the output rule is you take the set of signed messages, and if there's exactly 1, that is what you output. But since the honest sender will send you a signed message in round 1, and you cannot get another signed message from the other server, even if it's corrupted and tried because it can't break the signature scheme, there will be exactly 1 message signed, namely the one the honest sender intended to send. So that gives validity. Then there is agreement. There it said that all the honest servers should output the same. Or rather, I said if you have 2 honest servers that output something, those messages are the same, but that holds for all the pairs of the process. So it's all of them. But let's take out 2 honest ones and then compare it. We're going to go through a few cases. It's often where agreement easier to just do case analysis. Let's start with assuming S1 is honest. Then this follows from validity, as I said before, because when it's honest, the only thing that honest server's output is M. So the complicated case is the one where the sender is corrupted. Actually, let's do the bottom cases first. Let's assume that the sender is corrupt, S1 is corrupt, and also S2. Okay? What does agreement then say? It says that all pairs of honest parties should output the same. But there's 3 parties and 2 of them are corrupted, so there are no pairs of honest parties. There's only S3 being honest, so it should just agree with itself. That was easy. Right? So we see that sometimes stuff becomes easy when everyone is corrupted and a lot of them are corrupted. So there's actually only one interesting case, namely the sender is corrupted and S2 and S3 are honest. Now we would like to be sure that they don't end up outputting different things. Okay. But now remember that the protocol is the following. We have the 2 honest S2 and S3 here. Then I have a possibly corrupt guy up here that sends something to both of them. And then they swapped what they received. And then the output rule depended on their view. So they said, I have this view here. It was just, if there's a single sign message, that's what I output. But because the flow is like this, and then they swap what they have, they end up with the same view. The set of messages that they saw, it will be the same. If it's empty at both spaces. If it's exactly 1, it's the same at both spaces. If it's more, it's the same. What's important is it's the same view they have. So actually, any deterministic rule would have done, but in this case, we're just taking the one that gives us the validity, namely, if there's a single sign message, that's what they output. So they will end up agreeing. So it's a good protocol. And it's a special case of the so-called Dolive-Strong protocol that we will go into much more detail with. Sorry, I need to give this warning here again. Yeah, because the whole exercise, right, was to get to a point of trying to use the round-based protocol, and then also to give you this warning about safety violations by timeouts again. Notice that in the protocol here, we could have a safety property, let's say a prominent one, like agreement here. It could be violated if some messages are delayed. It's easy to see. I mean, in the protocol, we're relying on the fact that if the sender sends something to S2 and S3, and the sender is corrupted, then S2 and S3 will exchange their views and then make a rule, make a decision based on what they have. Now imagine if the sender up here sends a message to S2 and then it sends the message very late to S3 here, just before the next round begins. And we have been too aggressive when we set like the computation time. So verifying the signature and stuff over here takes a little bit too long. So it's forwarding maybe this message here too late. So it doesn't arrive over here before the deadline, so it's stopped. So S2 here says I didn't get a message from S3. So the set of messages I received is just the ones I got from S1. Then it might make a wrong decision. Because it could be that a contradicting sign message was on its way, but it didn't reach S2. So I sent sign F3 43 here. I sent sign 42 over here. This one gets exchanged. Maybe this one arrives actually. So party 2 that's sitting here sees, sign 42, sign 43. I output no message. But server 3 that's sitting here didn't get the contradictory one, has a single sign message and therefore outputs 42. So now they have outputted different messages in the system. And if this was now a state machine replication, they will start drifting apart. So that would be bad. So it means that a single kind of missed timeout turned into a safety problem, like the entire system became inconsistent. So the round-based model is dangerous in that. And in particular means it's also very slow, because when you decide on what should my timeout speed, they should be so big that no honest server ever misses them, like ever, right? So probably 5 minutes is not enough, right? I mean, depends on, what you mean by honest, but if we mean honest behavior is if my computer runs out of power, I try to get it up again and I should have time enough to get it up and then meet the timeout, then you need some pretty hefty timeouts, right? So if you have a protocol that goes through 100 rounds times 10 minutes, I don't even want to do that. That's a long time, right? That's days, maybe a week. Who knows? Whereas, I mean, if you are on a network where you typically do state machine replication, where these, let's say, 3 or 4 servers are tightly coupled on the network, a round might take milliseconds. That means if you have a protocol that goes through 100 rounds, it can probably be done within a second. So if you don't have timeouts, but always just progress as fast as the network allow you to exchange messages, which is what you do in an asynchronous protocol, then the difference is between something that takes a minute and something that takes a week. Okay? And it's because of this unfortunate thing that the second you start using timeouts, and in particular if you use them for safety, you have to set them big. Okay? So we try to not do that, except for didactic reasons, as we will do in the next video. Okay. And then the cliffhanger, okay? Because in the next video, I'm going to show you how to implement broadcast, not for 3 parties as we know how to do now, but for 4 and 5 and 100 and so on. And as you will probably realize, it's complicated. And it turns out, in fact, that if you want to do agreement with 100 servers, you will need to use a protocol that have 100 rounds. There's no easy way to do it. So this protocol that we just did of just sending and then comparing, it has 2 rounds, or 3, depending a little bit on how you count it. It won't do. If you have 10 servers, it won't do. So this thing of just having the sender send a message to everybody and then they compare and make a decision, it doesn't work. And since the next video will be very painful for you because of that reason, I would like to show you why it doesn't work. And then you can spend the time between watching this video and the next one thinking about how would you then fix the problem I show you now. Okay? So let's try to do broadcast now for 4 servers where we can tolerate 2 errors. I'm just going to add 1 server more. I'm going to try to tolerate the same number of errors. Remember, we know how to do this with 3 servers and up to 2 corruptions. I want to do it with 4 and just 2 corruptions. So in some sense, it looks like I should have made the problem easier because I have more honest servers. So let's see why it doesn't work. So let's try the same protocol. Let's say in the first round, the sender S1 will send M along with the signature to all the other servers. And then in the next round, each of these receivers, S1 up, S2 up to S4, they will forward what they saw to all the other servers. And then in round 3, we say, if I received in these forwards and in the original message, exactly 1 signed message, I will output that message, otherwise no, I will output no message. So why does that fail now? How can we make 2 honest servers output different decisions? I'll just give you 1 second to find the pause button if you want to pause it and think about it yourself, and then I'll skip on to the next slide and tell everyone else. Okay, you had your chance now. What I need is to have a corrupted sender and then 1 corrupted accomplice among the other ones. Let's see who I picked here. S2. Okay, so both the sender S1 and S2 are corrupted now. Okay. So I will have S1 send a signed message M to S3 and S4. So that will look honest to them. They'll just get 1 signed message, and that's what they will forward to each other. Okay. So that means if nothing else happened, S3 and S4 would now output M. They have seen a single signed message. But then S2 will sign another message, M prime, and forward it to its cheating accomplice there, S2. And then S2 will forward this signed M prime to S3, but not S4. Huh? It's annoying when you have a protocol with Byzantine parties, because they always find a way to make your life miserable. Right? And in this case here, we added a check. Right? We said, the sender could be cheating, so we add a check on what he sent. Right? Yeah, but now someone will cheat in the check. Then you add a check on the check. But then someone will cheat in the check on the check on the check. And in fact, that is why you will end up using 100 rounds when you have 100 servers, because you have to check the check of 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 the check. And we're gonna have so much fun with that in the next video. But this kind of boils down why it will get complicated. Whenever you do a check, someone will cheat in the check and so on. So you need a way to make that kind of settle down and reach an agreement. And in particular here right now, we see that S3 received two different signed messages, so it will output no message, whereas S4 has a perfectly clear view of the world and will output N. As you might imagine, adding another round won't necessarily help here, right? Because if you just ask S3 and S4 to exchange what they saw, then I'll just have S3 being corrupted instead and then lie to S4 in the last round. Or I'll just put in my stuff in the last round. That's where I will make your life miserable. So if you like combinatorics between this video and the next one, try to make that work with 4 servers, 2 of them that could be corrupted, and then make the 2 honest ones output the same, but be hard on yourself. You don't get to choose who is corrupted, right? So whenever you put in a check that there is no way to kind of cheat in the check and put in the inconsistency there.